Okay, so after all the stuff we had to do with series last week, which was kind of hard work, and it's not awful stuff maybe, but I think it's some of the trickier stuff that we have to do. Finally, this week we get to the big payoff in some sense. I mean, series are important in their own right. Okay, series play a big role in mathematics. So does getting ready by actually having everything secured to the wall. But, so series play a big role in mathematics. However, one of their most important roles is not simply as a series of numbers, but series defining functions. And we've seen this before, okay? I mean, what I would like to observe here is that the sum from, if we do the sum of AR to the N, well, this gives a function of the form A times 1 over 1 minus R when R has an absolute value that is less than 1. Okay, so we've seen examples where you can kind of think of a series as giving you a function. For a geometric series, it defines a function like so. And from this, you could get other types of series that define functions as well. For instance, if we wanted to do 1 over x, we could say, well, this means x equals 1 minus r. So, then we can figure out what does this mean? Well, this would mean we would be looking at the sum of A times, this would mean R is equal to 1 minus x. So this would mean the sum of 1 minus x to the n. And so we're able to sort of transform this into a power series that is equal to a different function. Of course, this only holds when the absolute value of 1 minus x is going to be strictly less than 1, but it allows us to express this function as a power series. And you can do other examples too. Okay, for instance, if I wanted to do, let's say, 1 over x squared, I could say, well, this means that x squared is equal to 1 minus r. That means that r equals 1 minus x squared, and then I would end up with a sum of a times 1 minus x squared to the n as my representation. So I can do this with different sorts of functions. Like, once I have a power series that represents one function, and I'm going to tell you what a power series is in a minute. It's not really that complicated. Maybe I should just say for the moment, once I have a series that defines a given function, I can then build other series to look at other functions from it. So, that's all well and good. Now, what I want to tell you here is what is a power series in general, because these power series are really useful for defining functions, but they are not the only way to define functions using series. There are other ways as well. For example, Fourier series define functions. And of course, there's others as well that you can use if you want to define functions. Anything where there is a variable in there will define a function as long as it is well defined. I know that sounds kind of redundant, but you know what I mean. As long as you get convergence, then it will be well defined. So here is what a power series is. It is a sum from n equals 0 up to infinity of some sequence b sub n times x minus a raised to the n, where a is some fixed constant. Now, power series are really useful in mathematics. In fact, a power series can be useful in mathematics even if it doesn't converge. But mostly we're going to be interested in power series that do converge in this class because we want them to define functions. Now, what can we say about the convergence of this series? Well, I want to take a look at the ratio test here. I think the ratio test is the easiest. You could also, if you wanted to, you could use the root test. But I don't know. I like the ratio test usually instead of the root test. But I think either of them will really work here. So we can say, or you mess around with the root test, but it's really going to tell you the same pieces of information as what we're going to get from the ratio test. Okay, so we look at the limit as n goes to infinity of the absolute value of bn plus 1 times x minus a to the n plus 1 divided by bn x minus a to the n. This is the limit as n goes to infinity of absolute value bn plus 1 over bn times the absolute value of x minus a. Okay, so what I want to observe about this is whether or not this converges and what it converges to only depends on this x minus a quantity, because our sequence of bn's, that is fixed. That's part of the definition of my power series, and it does not depend upon x. So the only dependence on x is a dependence on the absolute value of x minus a. Now, what is going to happen? Well, in some cases, you might find that this thing always converges. In some cases, you might find it only converges when x equals a. So one thing to note here is that this will always converge when x is equal to a, because in that case, we are literally dealing with a limit that is going to come out to be 0. So in fact, in that case, your series, all of the terms are 0 except the first one. So obviously it converges. We don't need any tests to tell us that. What we do need is to figure out why this is having such issues. What I really need is better tape, which I meant to get today and I forgot. Okay, give me a second because this is falling down. Okay, we're going to hope that this lasts for a few more minutes so that I can finish off this lecture. And hopefully by the time I do my next one, I will have better tape. Or some better way of getting this to the wall, at least. Okay, so it will always converge when x is equal to a. But the other thing that we can say is that it will be less than or equal to L when the absolute value of x minus a is less than r for some r. Or, I'm sorry, L will be less than or equal to 1 when this is true. L will be equal to 1 then when x minus a absolute value is equal to r, and then L will be greater than 1 if the absolute value of x minus a is bigger than r. The only exception to this is it might only converge for x equals a, or we could have convergence for all real numbers. So we might have that L is bigger than 1 anytime that x is not equal to a. Or we might have that L is always less than 1. Actually, in that case, you need to have L equals 0. But you could have something like that happen. But in the other cases, you're going to get absolute convergence when x minus a is less than r, or absolute value of x minus a is less than r. You're going to get, we don't know what happens when x minus a absolute value is equal to r, and then it diverges when x minus a is bigger than r. And an example of this sort of thing, I'm not going to work this out in detail, but if you look at the geometric series, you'll see that that's exactly what happens. It converges when you are between -1 and +1. And you can think of this as a power series with a equal to 0. Now, by the way, when you write the sum of bn times x minus a to the n, we say that this is centered at x equals a. And the reason we say it's centered there, well, there's two reasons. First of all, the a shows up there. But the other reason is because it converges when x minus a absolute value is strictly less than r. Now, this r depends upon the series. Like, you got to figure it out by using the ratio test or the root test. Like I said, you can do this with the root test too in a lot of cases. The root test will give you this same kind of thing. But because of this, the interval where you get convergence has a as its midpoint. So for that reason, we say it's centered at a, because, you know, it kind of acts like that's the center of it. Now, what we can say is then that capital R is called the radius of convergence. Now, you might think it's weird to think of a radius on the real number line, but it's kind of a radius, you know, it's a distance, and it's the same distance in all directions, of which there's just 2 in this case. So, yeah, it's a radius. In fact, you know, a one-dimensional sphere is a circle. A two-dimensional sphere is a regular sphere. Well, a zero-dimensional sphere is 2 points. Because if you think of a center, and you think of all the points that are some distance r from that, well, it's 2 points. So a zero-dimensional sphere is a pair of points. Anyway, the other reason we call this a radius is because it turns out that this works even if we allow x to be a complex number. It turns out that the same argument applies. So in fact, a power series will converge not just for real values of x, it will converge for complex values of x as long as their distance from a is bounded by r. Now, at x equals a plus or minus r, we need other checks on convergence. So you look at a power series and you want to know, where does this power series converge? Well, using the root test or the ratio test, I looked at the ratio test here, we can compute what is the r for which this converges. And anytime we are less than r away from a, it will converge. But at a distance of r, that's where things are questionable, because the ratio test and the root test fail us there. And because of that, you're going to have to use some other method. Now, methods that you can usually use to check include things like, maybe at one of these points you can do an alternating series test. Maybe at both of these points you can do an alternating series test. Maybe you can use some other trick. Maybe you can try to do, like, there's all kinds of little tricks that you can use. So you're just going to have to go back to all the stuff we talked about last week, kind of, and say which of these methods will work if x is actually a plus r, or if x is actually a minus r. And notice, it might converge at one of them, but not the other. So it could converge at, say, a minus r, but not converge at a plus r. That doesn't change the radius of convergence or anything, but it does change whether the endpoints are concluded in the interval of convergence. So the interval of convergence this is going to be the interval from a minus r up to a plus r, but the thing is, it might include the endpoints. It could include one endpoint and not the other. Why do I keep getting the plus wrong here? A minus r up to a plus r, or it could be that it has neither of them. So it might not converge at either endpoint. So you just have to check the endpoints separately. Now, the good news is that for a lot of purposes in math, we don't actually really care if it converges at the endpoints too much. We're mostly interested in the radius of convergence. But for some purposes, yes, it's important to know whether it converges at the endpoints. And like I said, you're just going to have to figure out a trick to use. Often, at least one of them, you might be able to do with an alternating series test. But again, you're just going to have to look at the specific example and figure it out. The other good news is that for a lot of the power series that we're going to be interested in, the convergence is going to be all real numbers, so we don't have to worry about endpoints. An example of this sort of thing, by the way, if you go back to the power series that we found for the geometric series, you'll notice that doesn't converge at the endpoints at all. So that one doesn't converge at either endpoint, which is fairly easy to check. And we've done that before, so I'm not going to repeat it here. You can go back and recheck what we did before if you are interested. Okay, so let's look at some properties of power series, because this is one of the most interesting things about them. Let's suppose that I define f of x to be equal to the power series from n equals 0 to infinity of b sub n times x minus a raised to the n. Now consider, and let's suppose, actually before we consider, let's say that we have a radius of convergence of r. And for the sake of this, of talking about radius of convergence, by the way, we often say that r can be infinity. Infinity is not a real number. So normally we frown upon saying that some variable is equal to infinity. But in this case, it's sort of okay, because all we're saying with r equals infinity is just that it converges for all real numbers. So because we aren't trying to do arithmetic with capital R or anything, we can allow it to be equal to infinity. We don't restrict it to just being a real number. So the radius of convergence here could be infinite, meaning it converges for all real numbers. Now what I want you to consider is the sum from n equals 0 to infinity of n times b sub n times x minus a to the n minus 1. Observation. This looks like a derivative of this, because literally what I'm doing here is I'm writing down the derivative of each term and I'm taking the sum. So, if you just looked at bn times x minus a to the n, what would the derivative of that be? Well, it would be n times b sub n x minus a to the n minus 1. For technical reasons, some people, actually we should probably say let's go from n equals 1, just because I want to make sure, let's start at n equals 1. That doesn't really change anything too much, but technically we don't want to have 0 minus 1 up here and get undefined at x equals a. So my apologies. That first term would normally just be 0 anyway, but it is undefined at one point, so we want to be careful. So this looks like a derivative of sorts. In fact, it would be a derivative if this series cuts off after some finite point. If the series cuts off after a finite point, so if these bn terms become 0 after some value of n, then actually f of x is just a polynomial. And in that case, this just becomes the derivative of the polynomial. So really, you can sort of think of this function as an infinite degree polynomial in some intuitive sense. Now, that's a very imprecise thing, so don't take it too seriously. Like, don't take that as a rigorous definition or anything. But yeah, in some sense, a power series is an infinite degree polynomial, in some sense. And in some sense, what we're doing is we're trying to write down the derivative of it. So that's where we're going with this. Now, let's look at convergence of this sum, not the original f. We already know this radius of convergence. What is the radius of convergence of this new sum? Well, once again, let's use the ratio test. I'm going to look at the limit as n goes to infinity of absolute value of n plus 1, bn plus 1, x minus a to the n, divided by n times bn plus 1, x minus a to the n minus 1. Now, this is, and I'm going to have to erase this to see what's going on here, this is equal to the limit as n goes to infinity of n plus 1 over n times the absolute, why did I put an n plus 1 there? I am so sorry, that should just be a bn. Absolute value bn plus 1 over bn, absolute value x minus a. But notice, this is going to approach 1. So this n plus 1 goes away. And this is the same limit as for the sum of bn times x minus a to the n. So we get the same radius of convergence. Now, at the endpoints, the convergent behavior could be different. So at the endpoints, you have to be more careful. But the radius of convergence stays the same. And I'm not going to prove this last bit to you, but it turns out that you can prove that within the radius of convergence R, the sum from n equals 1 to infinity of n bn times x minus a to the n minus 1 is the derivative of the sum from n equals 0 to infinity bn x minus a to the n. In other words, as long as we stay within the radius of convergence, we can take derivatives of power series by just taking them term by term, the same way as we would if it were a finite sum. Now, this is a really important fact, because when you are working with functions defined by power series, you may want to take derivatives of them, and therefore, you need to know how to do it. Now, like I said, if it's a finite sum, then it's easy, because then we're just dealing with a polynomial. So then we take the derivative the same way as we take the derivative of a polynomial, which means we go term by term. However, it turns out that within the radius of convergence, even when we generalize to this infinite power series, we still take the derivative term by term. This also has a very important implication for the usefulness of power series in mathematics. So why are power series so useful in mathematics? That is what I want to address now. Why are these useful? Why do we care? There are a couple of different answers. So, first reason that power series are important: solving differential equations. I'm not going to say a lot about this because we haven't talked much about differential equations in this class, but a differential equation is something where we have an unknown function and we have some conditions on the function and its derivatives. Like I might have something like 3 times the second derivative minus the first derivative plus 2 times the function is equal to 3x minus 1, or something like this. Okay. Now, in general, there are ways of solving these and coming up with closed form expressions as they're known. Often the solutions involve exponential functions. Coming up with the solutions can be very complicated though. And in some cases you can't do it. So one idea is you suppose y is given by a power series n equals 0 to infinity bn times x minus a to the n. And then what you do, often you choose a to be equal to 0, and then what you do is you write down what the derivatives look like, and you write down what this comes out to in terms of this infinite sum. Well, when you do this, we get conditions on the b sub n sequence. And what you do is you hope that you can then understand what goes on with this sequence. Now, the problem with trying to solve differential equations this way is it's really hard to evaluate a series. Even a power series, even a really well-behaved power series, is very difficult to evaluate precisely. Saying, this is the specific number that we get, yeah, that's probably not going to happen. It might happen in some cases, but it's pretty rare. Usually what we end up then having to do is, if we want to work with this function, we approximate it by cutting it off after a certain point. In other words, we approximate it by pretending that it's really a finite degree polynomial, or rather, we take the finite degree polynomial by cutting it off after a certain point. And there are ways of estimating how much error you will get in that sort of situation. Occasionally, though, you might actually recognize what this comes out to be equal to in some way. So this is one reason why people care so much about power series, is because sometimes you get a differential equation that you can't solve in any other way. I think this you can actually solve exactly, but I was just writing down an example of what a differential equation is. So for some very complicated differential equations, you might not be able to get an exact solution in terms of the functions we're used to, like polynomials and exponentials and trig functions, but you might be able to get the answer as a power series. Another reason why power series are so important is extending functions. So let's suppose that f of x is defined on some limited interval from c1 up to c2, or even maybe it's defined for all real numbers. So we're going to allow the possibility that c1 and c2 could be minus infinity and plus infinity as well. And let's suppose that f of x is equal to the sum from n equals 0 up to infinity of bn times x minus a to the n on the whole interval from c1 to c2. Well, if the radius of convergence is large enough that a minus r comma a plus r is bigger than the interval c1, c2, then what we do is we can consider this series as a way to extend our function in a way that makes sense, because on this interval, this series agrees with the function, and the derivative of the series will agree with the derivative of the function, and so on and so forth to all degrees, or all levels of, all degrees of derivatives. So like the second derivative, third derivatives, all of those will agree on this interval. But also, this series makes sense outside the interval. So we can extend the definition of our function off of this interval by using the power series. Now, when we're dealing with intervals of real numbers, this isn't super useful because usually our function on the real numbers will be defined on, like, there will be a reason why it's only defined between C1 and C2. So for real numbers, this is only moderately useful. Like, it only comes up in a few situations. However, this is where complex numbers come back into the picture, and this is where power series really show their power. Sorry about that terrible pun, but it's true. The really important thing is, in fact, what we can say is we can define f by this power series for complex x with absolute value of x minus a less than r as well. In other words, we start off with a function that is defined on some real interval. We find that on that real interval, it is given by a power series. Then we can actually extend the definition to complex numbers that are near this interval as well. Now, how near do they have to be? Well, that depends upon what the value of a is, and it depends upon what the value of r is. Okay, so that I cannot just tell you in general, but you figure out what your a is and you figure out what your radius of convergence is. That will tell you your answer. So you can use a power series to take a function that is defined for the real numbers and to define it for things that are not real numbers as well, to define it for complex numbers. One of the most important things that we are going to see, and we will see this next time, but I want to tell you now because I want to say kind of why we care so much about power series and where we are going with this. Here is a fact. E to the x, sine x, cosine x, these all have power series representations for all real numbers. So what this means is that there is a sequence b sub n with e to the x equals the sum from n equals 0 to infinity of b sub n times x minus a to the n for all real x. And in fact, we are going to calculate what this is next time. Why does this matter? Well, the fact of the matter is that means that this has a radius of convergence which is infinity. Well, what that means is that this series, and we still need to figure out what the b sub n's are going to be, but this series converges for all complex numbers as well. So what we can then do is we actually define e to the x by this series. We say, okay, for real numbers, of course, we define e to the x differently. We said, it's the regular exponential function, which is a little complicated to define, but, we define it in the usual way. But for complex numbers, we say, well, e to the x is going to be equal to this series. And that makes sense because the radius of convergence is infinite. And all of the properties of e to the x that we know and love continue to be true because they are true for this series. All of those usual properties you can show hold true for this power series. You can do the same thing for sine x and cosine x. You cannot totally do the same thing for some of the other functions we like, unfortunately. Like, the problem with tangent x is that it has places where it blows up to infinity and negative infinity. Things get complicated with that. You can sort of do it, but not totally. For things like logarithms. Logarithms give you a real problem, and I'm not even going to get into what happens with logarithms, but logarithms turn into quite a mess. It turns out that you can extend them, but you end up getting into really weird situations when you start extending them. So that is a problem that I will not deal with in this class at all. I will not even... Essentially what happens is as you try to extend them, it turns out that you have something, like, you can never extend them to 0, and also if you try to circle around 0, then your definitions become inconsistent with themselves. It's actually really interesting, but you have to take a course on complex analysis if you want to get into that stuff. So the point is, we are going to be able to use power series in the future to extend a lot of functions to the complex numbers in a way that preserves all of their nice properties. For instance, one of the properties that we should get is that the derivative of this thing should still be equal to itself. Well, when you define complex derivatives, you find that, yes, in fact, that property is preserved. And so these power series become really useful for this kind of thing. Now, the question that we now have to answer, and this is what we're going to do next time, given a function that we know, how do we find a power series representation for that function? The answer is, well, it's a little bit like finding linearizations of a function, except that we bump that up. So that instead of just finding a linearization, because what did we do when we do a linearization? We take f of a plus f prime of a times x minus a. And the reason we do that is so that the function and its derivative agree with the linearization and the derivative of the linearization at a. Well, what if we just insist on what is some power series such that the power series and all its derivatives agree with the function and all its derivatives at a? That's how we're going to do it. Now, the tricky part is then we got to show that the function and the power series are not just agreeing at a, but that they're agreeing away from a as well. And that is actually not even necessarily true. But for nice functions like e to the x and these cosine and sine, it is true. And the function will be equal to the power series. So that's what we're going to deal with next time. For now, I'm going to end things here.